Hello students, today we will be discussing on the material and enthalpy balance of an evaporator. Evaporation is a unit operation in which the weak liquor or the solution is concentrated by vaporizing a portion of the solvent to form a thick liquor. The feed in the form of weak solution is comprising of non-volatile solute plus volatile solvent. So solvent is generally water, but any other solvent may be involved in the unit operation. Here the heat supply with the help of the steam as a low pressure steam is being used as a heating medium, but any other heating medium can be utilized or to supply the heat. If we take, I have shown the schematic representation of this calendar type of evaporator where the feed is introduced with the solute concentration W wet 1% with the flow rate of EMF. Then at a temperature of Tf, then the heat supplied into the steam chest at a temperature of Ts to form the vapors with the flow rate of mV. Then the thick liquor obtained at a temperature of T with as the same temperature in the evaporator with the flow rate of m and the solute concentration W2%. Here if I write the overall material balance, the feed supply is distributed in the form of vapors plus the thick liquor obtained in the bottom product. So if further in the second equation, if I write the solute material balance, component balance, the solute in the feed is equal to solute in the thick liquor. So if I write here W1 into mm is equal to W2 mm. Further, the heat enthalpy balance. So first of all, the heat is supplied with the help of the steam. The steam is a low pressure steam. The heat supplied is that in the form of latent heat. So we write the EMS into product of the quantity of steam plus the latent heat of condensation of the steam. The enthalpy balance is written in the form of the heat input is equal to heat output. So heat in the feed plus heat in the steam is equal to heat in the vapors plus heat in the thick liquors. So if I write the equation, if heat in the feed is written in the form Mf plus Hf plus Ms m lambda s, that is equal to heat in the vapors plus heat in the thick liquor. So it just replace the mv as a difference between the quantity of feed and the quantity of thick liquor. The further equation is rearranged in the form of the heat supplied from the steam side is equal to Mf minus M, that is the vapors into enthalpy of the vapors plus enthalpy of the thick liquor into quantity of thick liquor minus Mf. So in terms of space, this is an equation, this is the enthalpy balance for an evaporator. In terms of the specific heat, if I write the heat supplied from the steam is equal to heat received by the weak solution to form a thick liquor and to vaporize the portion of the solvent. If I write here, the heat supplied from the steam is being utilized to increase the temperature from the temperature of the feed from temperature Tf to T, that is in the form of sensible heat. There is no change of phase of the feed plus once the boiling point or the saturation temperature is reached, then the further heat is supplied from the steam is used to vaporize the solvent from the solution. So that's why mv into lambda v. Here is mf in minus m. This is the difference, that is the quantity of the vapors formed is multiplied with the latent heat of vaporization. So for negligible boiling point rise, if I take the latent heat of vaporization of the feed solution is equal to latent heat of water, and we get it from the steam table at a given pressure. Then if I rewrite this equation, Ms Mf Cf K minus Tf plus Mu lambda. So with this use of this, we can also determine the quantity of the steam used to increase the temperature of the feed to its saturation temperature, and then the further temperature to vaporize the portion of the solvent. So there are the two terms used in the evaporation operation to indicate the performance of an evaporator, that is the capacity. capacity of an evaporator is the amount of this water evaporated per hour from this operation. And the economy of an evaporator is the quantity of the water vapors formed, that is the vapor that or the solvent vaporized per kg of the steam supplied. Generally, the single effect shows the less performance in terms of economy. This because the quantity, just because of this boiling point rise. So boiling point rise of the solution because of the impurities added into the solution. So the solution will not boil at the boiling point, but at a certain elevated temperature. So the difference between the boiling point of the solution and the boiling point of the pure water, pure solvent, is nothing but the boiling point rise. So further, in the design of the evaporator, the area of heat transfer in the evaporator can be determined by rewriting the equation in terms of overall heat transfer coefficient, where A is the area of the evaporator is written is nothing but equal to the heat supplied